Take-home quiz, here we go. A stream of protons is acted upon by a magnetic force while traveling perpendicularly. Hey, there is going to be a force because it is perpendicularly to a magnetic field, blah, blah. What speed are the protons traveling at? Well, I know that the magnetic force on a charge is QVB. As long as these are 90 degrees to each other, so my right-hand rule thingy works. Which they are, it says the magic word, perpendicular. They want the speed, okay. V is going to be F divided by QB. Did they give me the magnetic force? I see newtons, 5.8 times 10 to the negative 14th. Did they give me the charge? It's a proton, 1.6 times 10 to the negative 19. Magnetic field in Teslas is 0.6. Here we go, 5.8 to the negative 14 divided by bracket 1.6, negative 19 times 0.6. You get 6.04 times 1, 2, 3, 4, 5, 6.04 times 10 to the 5th meters per second. Number 2, a wire is, okay, they want the force on the wire, Mr. Dueck. The force, we said, on a wire was Bill, as long as the magnetic field and the current are all perpendicular, and they are, I double-checked. So, the magnetic field is pretty big, no, that's wrong, that's the current, Mr. Dueck. Where's the magnetic field? Oh, they want me to find the magnetic field, Mr. Dueck. It's going to be B equals F over IL, where the force is 2.4 times 10 to the negative 2 all over 5.2. Oh, Mr. Dueck, they gave me 2 lengths. Do I use the 8 or do I use the 4.2? I use the section of wire that's going to be experiencing the force. What's going to be experiencing the force? The total length or the chunk that's inside the magnetic field? The chunk that's inside the magnetic field. I'm going to use the 4.2 centimeters. Of course, I'm going to do the conversion of 0.042. I get a magnetic field of 0.11 Teslas. Is that right? Okay. What's the direction of the magnetic force? Okay, Vanessa, here we go. Right thumb in that direction, because that's which way the current is going. Magnetic field into the page, because that's what those X's mean. Are you telling me it's down the page? You'd be smiling and you'd be right. I like question 3, I like question 3, I like question 3. What is magnitude? Oh, okay, so first of all, the magnitude of the force on an electron is going to be QVB. Q, it's an electron. V, speed, 6.2 times 10 to the 6. B, 8.5 times 10 to the negative 3. The magnetic force acting on it, 1.6 times 10 to the negative 19, 6.2, 6, 8.5, negative 3. Is that right? 8.4 times 10 to the negative 15 newtons? Forced into a circle. Did they say forced into a circle? Why, that means that magnetic force is what's pushing me in a circle. Now, you could drop your answer down from part A into FB. I'm going to actually solve this algebraically. I'm going to say to myself, QVB equals MV squared over R, and yay, one of the V's cancel. They want me to get the R by itself. Well, this R is going to move to the top, and these are going to move to the bottom. I'm going to get R equals mv over qb. The most common mistake I see on this question is kids tell me that R equals qb over mv, which they cross-multiply wrong. They got 1 over R. It's going to be m mass. It's an electron. 9.11 times 10 to the negative 31. V, 6.2 times 10 to the 6th. Q, it's an electron. Magnetic field, 8.5 times 10 to the negative 3. What will the radius of this be? Is that right? 0.00415, pretty small. 4.15 times 10 to 4.15 times 10 to the negative 3 meters. What's the kinetic energy of this electron? Hey, you know what? That hasn't changed since Physics 11. Kinetic energy is a half mv squared. It's going to be a half m, 9.11 times 10 to the negative 31. V, 6.2 times 10 to the 6th. Thank you. My Physics 11s wrote their energy test yesterday. Oh, squareds, 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 squareds. Yeah. Do you get 1.75 times 10 to the negative 17 energy joules? Two marks? Okay. Number 4, what's the magnetic field strength? Okay, magnetic field, that's that. Oh, from a solenoid, I usually put a little SOL down there to remind myself I'm finding the magnetic field of a solenoid. Now, magnetic field of a solenoid, there's actually 2 formulas. There is this one, or there is that one. Which one am I going to use? Well, it depends whether they gave me the number of turns per meter, or whether they gave me the overall length. It looks like they gave me the overall length, so I'm going to use this one. The magnetic field is going to be the permeability of free space, 4 pi times 10 to the negative 7. N, the number of turns, 600. I, the current, 4.5, all divided by 0.032. So this solenoid would create a magnetic field of 0.106 Teslas. Want a stronger magnetic field? Either bump up the current or wrap more coils of wire around it. Or make the solenoid shorter. Can you give yourself a lovely score on this here quiz out of, is it out of 13? 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, it is. Give yourself a score out of 13, please. And then if you'd be so kind as to pass them inwards. Review. Last day we said, hey, if current can create magnetic fields, might magnetic fields create current? So we looked at the work of Faraday and Henry, and we said it turns out if you physically pull a rod through a magnetic field, the charges will be separated. You will do work separating the charges. In fact, you will feel a force opposing your pull, because nothing comes for free, and you'll create a voltage. That voltage was given by, BLV. Now I'm terrified. How'd the V, did I write the V down in your notes? Yet somehow it vanished. Oh, so did the word length of wire. Okay, now I'm really worried here. Oh boy, a bunch of stuff vanished from my notes. Okay, I'll be using, you know what? I'll use someone else's, a different lesson next. Anyways, I'm going to keep going here. It didn't vanish there. So we said, not only could we then calculate a voltage, you know what, and we used the archaic symbol EMF because we had a V and a V in the equation, otherwise tie, and that got confusing. We said, oh, if you hook up a resistor, and in fact, if you lay that rod down on some wires, you can get a full current flowing. We looked at some pretty cool examples. Oh, then we said, if you supply the current, you can get it to move. It's a rail gun. So we said, if you supply the movement, you can get a current. If you can supply the current, you'll get the movement. Get a rail gun. And I gave you some questions to try from the review, so I didn't give you any questions from here. I'll be giving you some questions from here on the last day before your test if you want to study, but otherwise, your questions right now, your homework is going to be from the review itself. So what we want to talk about is the generator. So in a generator, instead of us supplying current, we supply motion and get current. In a motor, we supply current and get motion. So I'd like you to imagine that we're spinning it, maybe over on this end, there's some kind of water turbine that's causing it to spin. We've got a water wheel hooked up on that end. That's the most common one, hydroelectric dams and hydroelectric power. I'm not going to include that in the picture, but we've mounted that to this. A coil of wire. In fact, this looks very, very, very similar to the electric motor picture. We have an armature. We have a permanent or electromagnet, doesn't matter which. We've got some brushes again. We've got some slip rings. What will this do? I'd like you all to draw a little positive charge sitting right there. There's our proton. Now, this coil is spinning in this direction. So right here, which way is this positive charge? Which way is this proton moving at that moment right there? I think kind of downwards. Right? So point your thumbs downwards. Right thumbs. Which way is the magnetic field? All magnetic field lines point from what to what? So downwards, magnetic field. You know what? It's going to feel a force. It's going to get pushed that way. Along the wire. Down the wire. Is that okay, Jake? And not only that, now you can't see it, but we'll put it right here. There's a proton right there on the other side of the armature. Which way is it moving? Well, on that side, it's moving upwards. Magnetic field that way. You know what? It's going to feel a force this way. In fact, what you're going to get is current. Oh, and then we just drain it off the end. Actually, what you're going to get is alternating current. Because as soon as this has made a half turn, then the proton that was moving away from us is going to be on this side, and now it's moving towards us, and in that same chunk of wire where it was moving away from us, the current is going to flip sides. It's going to flip directions, and this is why all of our infrastructure has alternating current coming from the plugs. It's so much easier to generate. It's so much easier to create. And then we have various clever devices, transformers and things, where we can turn alternating current into direct current. How does that work? We'll get there. So, the generator was invented by Michael Faraday. The previous figure shows a simple hand-operated generator with a coil consisting of only one turn to simplify the explanation. When the coil is rotated, the two long sides of the coil... Now, by the way, this section right here is parallel to the magnetic field, so no force will be exerted on it. Sorry. All of the action occurs on these two sides that are crossing, that are perpendicular to the magnetic field. So when the coil is rotated, the long sides cut across the lines of force, and a varying EMF of voltage is induced between these two segments. When the coil is vertical, right here, we have no voltage because right now this is moving parallel to the magnetic field lines. So for a split second, you'll have zero voltage. Right here, that's moving down the page, that's moving up the page, charge moving down the page, magnetic field points to the left. That's going to come out towards us, hence the dot. That's going to go away from us. We'll get a positive voltage. In fact, we'll get the maximum voltage when it's perpendicular to the magnetic field. Then, when we're right here, we get no voltage again, because this is moving that way, this is moving that way. Then when we're at 270 degrees, okay, we get a negative voltage because this side here used to be going away from us in this picture, but now it's exerting a current, it's inducing a voltage, it's sending protons towards us, so the current has flipped. In fact, what you really get is a current that does this. And those of you in pre-calc or in foundations may notice, yeah, it's a trig function, it's a sine wave. Which is why we don't look at alternating current in Physics 12, because we can't yet assume that you guys have seen trig functions. Pre-calc 12, you guys are starting to do trig yet? Have you looked at the sine graph yet? Certainly, I think you look at it in calculus, because it's got such a lovely derivative. Okay. What would happen if you spun this faster? You get a bigger voltage. What would happen if you spun it slower? You get a smaller voltage. Now, Faraday wanted to come up with a way to link spinning with E equals BLV, inducing an EMF by pulling a rod through a magnetic field. By the way, here's a big explanation of what I just said. So, here's the question that Faraday wanted to get to. How can we combine induced voltage in a wire and induced voltage in a loop of wire? Consider the following example. So I have situation A, B, C, D, E, and F. And the magnetic field looks like it's coming. Oh, what do those dots mean? Which way is the magnetic field? Okay, magnetic field's coming out of the page. So we're moving a coil into a magnetic field and out of a magnetic field. Where will there be an induced current? Well, look at situation A and situation F. Is there any external magnetic field in those locations? So you know what? Let's cross those out. There's no B. And I'm going to argue situations C and D are the same. Let's look at those. But I think they're both really just the same picture, a little bit before and after, but they're inside the magnetic field. So let's look at situation C. Don't write this down just yet. This and this, since this is moving that way, those two chunks of wire are moving parallel to the magnetic field. Will we induce a current from those? No, and you can double check, because if I just draw my little proton right there, charge moving that way, magnetic field out of the page, it'll get pushed down, and it'll get pushed down, but that wire is so thin, you're not really separating any charges. Let's look at a proton on the back part of this coil. This is moving to the right, so all of you point your thumbs to the right. Magnetic field which way? Out of the page towards us. I got to kind of do a yoga bend, but that's, you know what? This proton will get pushed down the page, and so I think to myself, oh, maybe we'll induce an EMF in location C. However, what if I look at the proton on the front of this coil right there? Which way is it moving? To the right? Which way is the magnetic field? Out of the page. Which way will it feel a force? Also down the page. You know what? If you have two batteries pointing towards each other that are the same size, what's your net voltage? What's your net EMF? 0. Situation C and D, you're not going to get any EMF either. Let's look at situation B. Now, notice in situation B, when we're just entering the magnetic field, we got a proton there, we got a proton here. Although this back proton, is it in the magnetic field at all? So will it experience a force yet? No. I'm going to worry about it. You can leave it there. You can cross it out if you want. This front proton, which way is it moving? To the right. Point your finger to the right thumb to the right. Which way is the magnetic field? You know what? It's going to feel a force down the page, and there is no opposing force from the back side of the coil. As we enter the magnetic field, we're going to create a clockwise current. Current will flow in that direction. We are going to induce a voltage and a current. Once we're totally inside the magnetic field, situation C and situation D, the voltage is going to drop to 0. What about situation E? Now in situation E, only the back part of the wire is inside the magnetic field, but it is still moving to the right. So point your thumbs, right thumbs to the right. Magnetic field coming. You know what? I think it's going to be pushed down, but there is no opposing force, Emma, on the right part because that's out of the magnetic field. I think we'll get a counterclockwise current. Marissa, are you noticing we get an alternating current? It was clockwise on the left. It went to 0 when we were totally enveloped, and then it's counterclockwise on the right. We're getting a current that changes direction. Faraday thought for a while. He says, I got to be able to explain this too. I want one theory, one concept that can explain the pulling of a single wire, the spinning of a coil, and the moving of a coil into and out of a magnetic field. So you okay with the why it's B and E? What's the difference there? And this is where I take my hat off to Faraday and I say, brilliant. He says, I think I got it. To explain this, Faraday realized that a voltage, and therefore a current, in a coil was induced when the area of the coil that was exposed to the magnetic field changed. He said, what's changing here is not the area of the coil, not the size of the coil, but how much of that area is being exposed to the magnetic field. How much of the area is being exposed to the magnetic field right now? 0. What about if I go 1 centimeter sideways? How much of the area is still being exposed? 0. What about between C and D? All of it and all of it. Now you might say, well, why isn't there a current? He said, no. It's not how much area, it's if there's a changing area. If the area that's being exposed is changing. And he said, that's why B and E give you a voltage, because B, you're going from no area to max area exposure. That's a change. And in E, you're going from max area exposure to no area once you've left the magnetic field. That's a change. Here is your final unit of the year. This is it. So this leads us to the concept of magnetic flux. Magnetic flux is the number of magnetic field lines passing through an area. Okay? Symbol. Really? I was doing so well. Symbol. Technically, it's Star Wars fans will recognize a TIE fighter on its side. Although, when you get in a real rush, we just do that and we don't put the little hash marks on the top and bottom. Units. Well, there's different types of flux. So this is magnetic flux. All flux is measured in lines because it's always the number of lines. There's electric flux, which is the number of electric field lines passing through a given area. There's all sorts of different flux out there. But magnetic flux is measured in Webers, 2Bs or 1B, can't remember. It's measured in WB. How do we calculate it? You take the magnetic field and you multiply it by the area. Oh, except these have to be perpendicular to each other. Put your pencils down, look up. A great way to think about magnetic flux is to imagine a flashlight and a circle passing through the light. Here, my projector is my flashlight. instead of thinking about magnetic field lines, instead ask how much light is going through this circle. So how much flux, what would the flux be right now? 0. What happens as the area approaches perpendicular to the light? Maximum flux. And 0. How else can I change the flux? Well, there's several ways. If instead of this roll of tape, I use this, which has more light passing through it? This or this? The hoop. Okay, so one way is make the area bigger. Okay? It doesn't have to be circular. You can make a rectangular area or whatever. But in our case, this year, it's going to be either a circle, pi r squared, or a rectangle, length times width. We're not going to get all funky. You can do that next year in calculus. There's another way. I could make the, in my case, flashlight stronger, or in this case, magnetic field stronger. How do you make the magnetic field stronger? If you get closer, watch. What do you notice about the shadow? What do you notice about the number of magnetic field, what number of light lines going through it? More. So one way to increase flux is to move closer to a magnet. The other way, and I can't demonstrate that, would be to put a larger bulb. Oh, wait a minute. Magnetic field of a solenoid, B equals mu naught N times I over L. Mucking around with those, you can bump up the magnetic field of the solenoid. Okay? So magnetic flux, all flux is the number of lines passing through a given area. And that's why you can see I added the perpendicular. Now, we could say, what if it's slanty? You would take a trig component. You would actually use a vector component. And those that do physics next year in post-secondary, you'll look at it there. But this year, it's either going to be all or nothing. 0 flux, full flux. Okay? Again, apologies to people at home on YouTube because they're going, what the heck was he talking about? Sorry. What can you tell me about the flux, the amount of flux passing through each loop? So this is a side view. Well, which one has maximum flux, A, B, or C? Which one has no flux? And this would be some kind of middle amount. And for those of you who are wondering, what you could really do is you could go like this, and you would get an angle theta right there, and it's a trig component. I can't remember whether it's sine or cosine. I could derive it if I really wanted to, whatever. Turn the page. So remember, we said this. Flux is equal to magnetic field times area. Describe whether the flux is increasing, decreasing, or constant in each case. So, in situation A, I'm not changing the area, but I'm increasing the magnetic field. What will that do to the flux? Okay, here, the flux increases. That would be the same as this situation, right? So B, what if I decrease the magnetic field? Okay, flux decreases. What about here? If the area inside the field decreases, what's happening to the flux? Okay. Now, in those three examples, were any of those a constant flux? Then in every one of those, we would be inducing an EMF, we would be inducing a voltage, and therefore get a current. This was Faraday's leap. I got it now. We're going to come back to situation D in a second. Situation E, we're moving that coil inside the magnetic field. What do you notice about the number of magnetic field lines coming through it? Increasing, decreasing, or staying the same? Staying the same. That's why you will not get any induced voltage here. And this was because for the longest time, scientists couldn't figure out why this coil thing wasn't working. They didn't think to change the flux. They were saying, well, why wouldn't I just go maximum flux? Shouldn't that give me And they'd get a brief blip and then wonder why it stopped. So here, flux is constant, no EMF. What about in situation F? If I move the magnet towards the coil, what's that the same as? Moving the coil towards the magnet. What's that the same as? Increasing the magnetic field. You're going to have an increasing flux. And now we're starting to link a spinning coil. Because if you spin this coil, so we're going to start off like this, what's happening to the shadow? What's happening to the flux? Decreasing. And that's how I kind of imagine flux, as the shadow that I would see on the wall from a flashlight shining through a little hoop, little circle. But here's the important part. While that flux was decreasing, you would induce an EMF. What about in situation H, where you're squeezing the loop smaller? Decreasing flux. But again, the fact that it's not constant, I'll get a voltage. I'll get an induced EMF. What about, I? If we increase the current, do wires create magnetic fields as well? Yeah. In fact, this is going to be the first right-hand rule that I showed you. We're going to look at this wire. Ignore that coil for a second. Point your right thumbs in the direction of the wire. Which way is the magnetic field created by the wire? Well, on the top, I think it's going into the page, but on this side, I think it's coming out of the page. Is it not, if your fingers curl this way? What happens if you bump up the current? What do you think happens to that magnetic field? Increases. What do you think happens to the flux in the coil then? This is an... Now remember I said, Ty, Faraday was going to link pulling that rod on the rails from last day to spinning a coil. Let's go back to example E. Here's what he had. Here's what he realized. He says, there is an area in situation, I said E, situation D. There is an area. It's the area behind the rod. As I pull the rod to the right, is that area increasing or decreasing? He said, you know what? The flux is increasing. I never would have thought of that as an area in a million years. Gotta love Faraday. Not only that, but he then also came up with an equation. Although I told you the other day his math skills were so poor, he wrote it out in English and had somebody else translate it into an equation. But previously, I said that an induced voltage was created when I changed the field or the orientation or the area in the field. I can summarize all that. Voltage is induced when you have a changing flux. Voltage is not induced when you have a constant flux. Faraday found that the amount of voltage varies directly with the flux change, bigger change in flux, bigger voltage. Inversely with the time, if you change the flux quicker, you get a bigger voltage. Smaller time, bigger voltage. Slower time, smaller voltage. And directly with the number of loops of wire if you're doing a coil. If you want 100 times the voltage, instead of using one loop of wire, use 100 loops. And now we can already, Shelby, talk about exactly customizing how much voltage that I want. I can change the area. You know what? It's actually just easier to change the number of wraps of wire around the given area and how fast I spin it. Here it is. Faraday's law. The induced EMF, the induced voltage, created in a coil or coils of wire is given by, put an equal sign there, leave a small space, N, change in flux over change in time. But the reason I said leave a small space is in front there's a negative. Why negative? Tune in Wednesday. where N equals the number of coils of wire. Flux equals B times A as long as they're perpendicular. Oh, but it says change in flux. Now, you know why all those months ago I said, hey, what's changing anything? Okay. Oh, and change in time equals change in time. By the way, time is always a change in, and you notice over the most of the time, no pun intended, I get sloppy, I don't put the delta. It's traditional to put it there just because it makes it nice and symmetrical and pretty. Honestly. Okay, let's do an example. A circular loop of wire of radius 2.5 centimeters is in a magnetic field of 0.4 teslas. If the loop is removed, you know what, that's probably important, from the field in a time of 0.05 seconds, what's the average induced EMF? Okay. Now, if we have a straight wire, don't write this down. Christine, if we have a straight wire, we would use this. If we have a coil, we're going to use Faraday's law. The induced EMF is equal to negative N, change in flux over change in time. And this is one time, Vanessa, it's worth dulping. It's worth listing your data over on the side. So first of all, in this question, what's N? And I'll give you a hint right there. 1. Okay, look for the pronoun 1. Otherwise, they'll tell you how many. But if they say loop, that's 1. Yay, makes it easier. Change in flux. What's change in anything? So I'm going to write here flux final equals and flux initial equals. Flux final is pretty easy to get. Look up. Here's flux final. 0. Right? No shadow anymore. Initial is going to be magnetic field times the area. They are perpendicular to each other. I looked at the picture. How big is the magnetic field? 0.4. How big is the area? Now, this is the area of a circle. Mr. Dueck, it would be wonderful if on our formula sheet you had been so kind as to include the area of a circle. I think I did. What is the area of a circle? It's pi r squared. Don't go 2 pi r. It's pi r squared. So it's going to be pi. Please tell me I told you the radius. I did. 0.025. Carly? Squared. Okay? Don't reach for your calculator just yet. Seriously. And what's the time, Carly?
0.0.
Okay. You can crunch the numbers separately, or you can just drop this all in. You can say, okay, negative. I'll write the 1. Normally I wouldn't, but in our notes, Emma, so that I know that I took care of it, we will. The change in flux is final minus 0.4 pi 0.025 squared all over 0.05. You could do that inside bracket, the change in flux first separately, Carly, if you want to, and then use your answer button. Or you guys can go all in one fell swoop. I really don't care. If it's more complicated, if both fluxes aren't, if one of the fluxes isn't 0, then I'll crunch it separately. How many volts are we going to get here? Well, let's see. Negative 1 times, I know I didn't need to write the 1, 0 minus 0.4 pi times 0.025 squared. Close off that. Divided by 0.05. You get 0.0157 volts. Not very big. Well, it's only one loop. 0.0157 volts. Yep. Let's kick it up a notch. A square coil of wire, 5 centimeters. Oh, you know what? Square. What's the area of a square? really length times width, but since they're identical, if you really wanted to, you could just say length squared. Oh, is that where the term comes from? Yes, Captain Obvious. It has 100 turns. It lies perpendicular to a magnetic field. So it's starting out perpendicular to the magnetic field, and then it's rotated 90 degrees. Oh, what's my final flux going to be? 0? Okay. What's the average induced EMF? Negative N, change in flux over change in time. N equals 100. I usually do N and T first because they don't take any work almost always. The time is 0.002, and then I save some room to carefully crunch the change in flux. What's change in anything? So I usually go flux final, which in this case you guys told me is 0. Flux initial is going to be BA. B, 0.02. A, 0.05 squared. And again, if you want to crunch that and write it as a number, you can. Or you can now carry all this over into the equation. You can say negative 100 final minus initial all over 0.002. Did I make a mistake? No, we're good. I think this one you get a little more impressive voltage. Negative 100 times 0 minus 0.02 times 0.05 squared divided by 0.002. Oh, 2.5 volts. Yes? Now we're approaching a battery. What if you wanted to generate 5 volts instead of 100 turns of wire? Use what? It's that easy to customize your voltage now. Or turn it faster or change the area, but the easiest one is just more wire. We can also change the flux by changing the magnetic field. So far, we've been changing the area exposure by spinning it. We can also, in fact, flip or change the magnetic field. However, magnetic field is a vector, which means if you go from being to the left and then you end up to the right, or if you go from out of the page and you end up into the page, you better let one way be positive and one way be negative. Okay? Oh, I like this example. I like this example. I like this example. This example is a nice question. A circular coil with 100 turns of wire is exposed to a changing magnetic field. So now the coil isn't moving, the magnetic field is. If the field takes 0.12 seconds to change, what's the average induced voltage? The average induced EMF? Okay. What direction, Jake, is my magnetic field in the before picture? Into the page. What direction is my magnetic field in the after picture? One of those is going to be positive. Pick. I don't care. Pick. Okay, this is going to be positive, and this is going to be negative. Okay. So we've decided to go with Jake's induced EMF. By the way, the reason I'm saying average induced voltage all the time is because, remember I showed you it's a sine wave. It is actually changing constantly, so we're finding an average voltage. Negative N change. Why negative? Tomorrow over change in time. Over here, let's list my data. N equals 100. T equals 0.12. Okay. Flux final is not 0. It's going to be B times A. It's going to be B final. That's what's changing. Times A. Right? Jake, what's my final magnetic field? Why is 5.4 wrong? You just decide. You told me that's going to be negative.
7.8.
No. You told me it's going to be negative. Okay, then let's be consistent. So negative 5.4. By the way, huge magnetic field. Area. What shape did they give me, Jake? You know what? That's going to be pi r 0.1 squared. Flux initial. It's going to be B initial times A, because the area is not changing this time. The magnetic field is changing. Oh, and also, Vanessa, you'll notice I'm being way more careful. That 0 in the previous questions allowed me to be pretty casual, because I knew I was going to get one of them right. You know? Magnetic field. Jake, what's the initial magnetic field?
7.8.
Positive? Are you positive? It is positive. I'm positive. Okay. 7.8. Very huge. Times pi times 0.1 squared. So I'm even going to put here the change in flux. Let's go to my calculator right now. It's going to be 7.8 times, oh, no, final minus initial. You know what, Mr. Dueck? Just because of that, you better write that. Final minus initial. It's going to be negative 5.4 times pi times 0.1 squared minus 7.8 times pi times 0.1 squared. You got a change in flux of negative 0.41469, blah. So I'm going to write negative 0.4147, but I'll keep this number on my calculator. Units for flux. Webers. So that's going to go over here. Alrighty. The induced voltage is going to be negative 100, negative 0.4147 divided by 0.12. Negative 100 times answer button divided by 0.12. Oh, hey, now we've got a generator. 346 volts. That's something. That'll power stuff. 44, Mr. Duke? 346 volts. Okay. Now, McKinley, you could have, if you had wanted to, decided to let final be positive and initial be negative, and you'd get negative 346 volts. And I'd give you credit because there is no frame of reference to define which one is positive, which one is negative. You'd get full marks. I did like Jake's suggestion because as soon as he let the final be negative, I knew that we would have a negative take away a positive. We'd have a negative flux times the negative in front gives me a positive answer, and you've had me long enough to know that I know I make mistakes with negatives. I'm always happy to get rid of them, but they're both fine. Example 6 says, rank the 4 loops below in order of increasing induced voltage. So from smallest to biggest. Okay? One of these has no induced voltage because there's no change in flux. Which one? B. So B equals 0 volts. Which one of these has the next smallest change in flux? And you kind of have to guess, but I added 2 words to make it a bit more obvious. Yeah, squeezed a bit. That's my way of saying, oh, not much. Okay? Certainly, between A and C, I can tell you which one will have a bigger flux change and therefore a bigger voltage. Which is the biggest? I think A goes from full to none. C goes from full to some, right? So I think C is next. A will have the maximum induced voltage. because it's got the maximum change in flux. And remember, flux is the number of magnetic field lines passing through a given area. So, technical comment on induced voltage. For moving wires, it's best to use, for coils, it's best to use coils, wires. Okay. Although you could use Faraday's law, this one, because I told you it's actually the area behind the wire that's what's changing, and there is a way to crunch all that, but it really, you need calculus, and we'll leave it alone. What's your homework? Again, I'm not going to assign questions from this. I'll assign some later on for your studying, but from review, you can now do number 5. I like number 5, I like number 5, I like number 5. "11 is really tricky, but very cool. So it turns out, if you look at number 11, it's a helicopter rotor, and this is actually apparently an issue that search and rescue has to deal with. The propeller spinning can be thought of as a bunch of protons locked in a coil of wire spinning through a magnetic field. Which magnetic field? The Earth's magnetic field. And apparently those propellers can generate enough of a static charge that if they lower a metal cable down to somebody on the ground, it can arc and they can actually get a shock. They have to take this into account and discharge it. See if you can figure out number 11. I'm only including it because it's nerdily cool. You can look at my answer key online if you get stuck. It is tough. "12 is fair game. "15 is fair game. Now in number 15, they're asking you in the part B to find the magnetic flux. You know what? They don't tell you the magnetic field, but they give you the solenoid and what's going. You can use that to find B to then go B times A. 16 is good. "23 is good. 24 is good. "32 is good. 34 is good. 364, Mr. Dueck. 34 is good. 36 is good. 37. 39. 40. 46. Those are all questions that use flux.